You're welcome to day 47 of 50 days of tutelage. In today's class, we'll be talking about DC circuits. First of all, what is a circuit? A circuit is simply a closed path in which electric current is flowing through. So any path of this nature, any path of this nature, any path of this nature, as long as the path is closed and electric current is flowing through it, then we have a circuit. Now, so what now makes a circuit? What makes it a DC circuit? A DC circuit is a circuit in which the type of current that is flowing through it is a direct current. DC, direct current. Now, direct currents, they flow in only one path. They flow in only one direction. So when you have a direct current, it means that if it's going like this, it's going like this. So it's unlike the other one, which is the counterpart, is called alternating current. That one actually varies in direction at different time. That is not our business in today's class. So we are only going to be focusing on this DC circuit thing. So direct current flows in what? In one direction only. And when you say a DC circuit now, it is a path that has a closed path in which a direct current is flowing. So that's basically what we have. So I'm going to be telling you about so many things. What is electric current itself? So electric current, from what you know already, is the rate of flow of electric charge. So which is why you have electric current as Q divided by what? Q divided by T. So you have Q equals IT. So this is electric current. Is simply the rate of flow of charge with respect to time. Another thing we also take note in the circuit is that we also have what we call the potential difference. We have the potential difference. Potential difference, which is represented using V, is simply the work done per unit charge. The potential difference is simply the work done per unit charge. Potential difference is work done per unit charge. So we have all of these things. So I'm going to be explaining everything when we get to analyzing of electric circuit itself. So I'm just introducing you to some of the few concepts that we're going to be using in it. By the way, talking about this potential difference, there's something we call terminal PD, terminal potential difference, and there's something we call e.m.f. These two, they are attributed to a cell. So let's say you have a cell now. So let's say this is a cell. Now this is just an example anyway, so it doesn't really matter. So this is the positive terminal and this is the negative terminal of the cell. So what do we mean by terminal potential difference? What do we mean by e.m.f? You see, the thing is that for the e.m.f of a cell, the e.m.f of a cell is the actual value of the work that this guy is capable of doing. In fact, you can call it a form of energy, a stored energy in this cell. So this guy can be, let's say, 20 volts. So it has e.m.f of 20 volts. That is, it is capable of supplying 20 volts. But the problem now is that if this e.m.f has what we call internal resistance is just like the way for normal work done. So for normal, anyway, PD is always work done. For normal work done, we have what we call work done in overcoming friction as well. So when there is internal resistance, it is just like friction in the cell as well. So this, to overcome this internal resistance, you would actually have to do a certain amount of work as well. And the work that you have to do is denoted as IR. R, small r representing internal resistance. So when you do this work now, it will be removed from the 20 volts. So let's say it is everything here is equivalent to 2 volts. So therefore, what you have left is 18 volts. So that 18 volt is what will be supplied at the terminal of this guy. And that will be what your terminal PD will be. So the terminal PD here will be what? 18 volts. So therefore, the sum of the terminal PD and the energy that is required for the internal resistance will be equal to the e.m.f. So this terminal PD is also denoted as I times external resistance plus this equals e.m.f. So take note of that. I think I've been able to explain that very well. Then what is resistance itself? Resistance is simply the opposition to the flow of current. Resistance is opposition to the flow of current. And that leads me to Ohm's law. So what does Ohm's law say? Ohm's law simply says that current is directly proportional to voltage at constant temperature. So with this relationship now, we introduce a constant of proportionality. In this place, we know that if we say I is proportional to V, then we have to introduce a constant in a way. So when we introduce a constant, the constant we introduce is the resistance. So this is resistance. And I'm going to show you about this resistance. We have what we call a series connection, and then we have what we call a parallel connection. So I'm going to explain how we sort that out in this particular video. So if you have, let's say, a connection, so let's even start with a circuit. Before I go into the series and parallel connection, let me quickly define the three types of circuit that we have. We have what we call an open circuit. We have what we call a closed circuit. And we have what we call a short circuit. So for an open circuit, what happened is that you have this connection. So I'm just going to let's put a battery here. And then around here, you have what we call a key. You have what we call a key around here. And in this place, you have a load. So yes, this is load L. I'm just going to copy the same guy and paste it in the other place as well. So let this one be here. And let this one be here. So what is an open circuit? Now, this perfectly defines an open circuit. An open circuit is simply a circuit where current is not flowing. So if current is not flowing in a circuit, then you have an open circuit. It simply means that, as you can see here, the switch is actually closed. So because the switch is open, so therefore current will not be able to flow in this place at all. Current is not flowing in this whole place. So the load will not be powered. So if this was a bulb now, the bulb will not light up in this place because current is not flowing. So it's an open circuit, the key is closed. But if you want a closed circuit is one in which this key is closed. So because the key is closed, current is then flowing through it like that. So as current is flowing through it, this load will be powered. So therefore, you have light in this system. But what do we mean by a short circuit? A short circuit, for this setup that I've made now, a short circuit is going to be, for this particular setup, please take note. If you close this now, you close this place, and then you remove the load. You close it and you remove the load. So this path is just a normal path like this. As you can see now, this guy is not delivering, the current is flowing, but it's not delivering current to an external load. So with this now, you have what we call a short circuit, and therefore there can be damage in this system. But at the same time, there can also be load in this system, not this kind of setup now. That is, maybe you have another loop like this, and then you place a load somewhere around here. So what happens is that currents usually take a path of low resistance. Currents like to take a path of low resistance. So this is the thing. Current in this place, it has so let's say the battery is even here, in the middle here. I think I should do this instead. So let the load be here. This is the load. Of course, load is, like I said, resistance is opposition to the flow of current. So therefore, this load is going to offer a resistance. But when you look at the wire that you have here, there's no load in this place. So the current has two options, either to go this way or to go this way. Now, if it goes down like this, it's going to power the load. If it goes, but with high resistance, if it goes up now, it's going to be with low resistance. So current like to travel through the path of low resistance. So therefore, it goes this way instead. And it can cause this guy to be damaged. There can be a spark, there can be a sort of overheating, and different things like that. And this load will not be powered in that system. So the best way to define a short circuit will be that a short circuit occurs when current takes a very low resistance path bypassing the load if present. So if load is present, and then there's another path for current to travel through, then the current is going to go through that path and bypass the load, and therefore it can lead to overheating, it can lead to sparks, and it can lead to damage of the cell or of the entire system. That's very dangerous. You shouldn't try making a short circuit, by the way. So back to series and parallel connection. So for series and parallel connection, I will first of all talk about when cells are connected in series. When cells are connected in series, this long side is the positive terminal of the cell, and this small side is the negative terminal of the cell. So when cells are connected in series in this manner, so when you have cells connected in series like this, you have other cells like this, and they're connected in series. So if this is V1, if this is V2, and this is V3, so the total cell, the net cell that you have here is going to be V1 plus V2 plus V3. So take note of that. Now, however, if these cells are connected in such a way that you have something of this nature, you have something of this nature, you have something of this nature. So what you notice here is that a particular cell is actually in reverse direction. So two of them are in the same direction. So V1, V2, V3. So the next cell here will be V1 plus V3 minus V2. So direction really matters. So positive to negative, positive to negative, positive to negative. So they are well aligned in this place. This one is a reverse direction in that situation. But how about when cells are connected in parallel? When cells are connected in parallel, so what even makes them to be parallel is, so you have something of this nature, you have something of this nature, you have something of this nature. So you have this, 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 and you have this. So what we notice is that if this is V1, this is V2, and this is V3, so one would think that, oh, the total will be V1 plus V2 plus V3. There's actually only one voltage. In fact, whatever the source is, whatever the source that we're dealing with, this will be V1 equals to V2 equals to V3. V1 equals V2 equals V3, and it is the same thing as the total voltage in the entire system. So I'm going to explain this thing when I get to the place of resistance. So V1 equals to V2 equals V3, and that is for voltage. So you need to take note that in when we have parallel cells like this, V1, V2, V3, we don't try to put cells of different EMFs. We don't try to put them together in a parallel connection. We put cells of the same EMF. So if this one was 3 volts, this one will be 3 volts, this one will be 3 volts. And it doesn't mean that their total will now be 9 volts. Their total is not equal to 9 volts. Their total will also be 3 volts as well. So we have V1, V2, V3, they are equal and equals to the total voltage as well. So now let's talk about resistors in series and parallel. So if you have resistors in series, so you have something of this nature, and then so this is for series connection. Resistor 1, resistor 2, resistor 3. So the total resistance in this place is going to be R1 plus R2 plus R3. That's how you add resistors in series. Then if you have resistors in parallel, so let's say you have these 2, 3, then you have something of this nature, something of this nature, something like this, like this. So you have your R1, R2, R3. So what happens is that the total resistance, the inverse of the total resistance, equals to the sum of the inverse of each of those resistors. So 1 over R2 plus 1 over R3. So you solve this whole thing and you try to solve for your R total in the process like that. That's how you handle resistors in parallel. However, you can have a situation whereby you have both series connection and parallel connection. You have to properly analyze them together. And what determines that something is parallel is not necessarily because they are, on top of each other like this. They can actually be on top of each other and they are still in series connection. So what determines it is actually when you trace the movement of current. So if you get to a junction where current is splitting, so if you can see now, this place now, if current is traveling at this point and it gets to this junction, it will have to decide whether it will go like this, or go like this. So therefore, those three parts, anything that is in their way will be in a parallel connection. So if you have something of this nature, so you have a resistor here, you have a resistor here, and then you have this connection like this, you have this connection, you have this connection. Of course, the battery is somewhere around there. I'm just trying to explain something here. So you notice that if they say the battery is here, so current will go through this place. Then later we pass through this place. So these two, even though they are on top of each other, they are in series connection because there's no confusion of, I want to pass through a path or I want to pass through this other path and all of those things. So the way series connection works is that if you choose any two guys and if they're going to be in series connection, just look at it very well. Current will pass through one before it enters another. So that is how you know a series connection. By the way, I have made a detailed video on how to properly analyze a circuit, series and parallel. I made use of a very complex circuit connection. So you can just check the pop-up right now that is popping up. Go through that link, save that video, and watch it later. I analyzed a very complex circuit in that video. It will help you understand the whole idea about circuit and then how to analyze series and parallel connection, even their combination. It will help you analyze them together. So let's move on. Now that I've been able to discuss that, the next thing I want to discuss is the concept of Kirchhoff's law. So for this Kirchhoff's law, I want you to pay attention very well. It's one of the places where students actually get it very wrong. So basically, what Kirchhoff's law is saying is that there are two rules to follow. Roman figure one is that if you have any junction, in an electric circuit, the summation of all the currents there will be equal to zero. And when we say summation of all the currents there is equal to zero, some currents will have positive sign, some will have negative sign. Why? For the one that has positive sign, they are the one that is entering that junction. The one that will have negative sign, they are the one that is leaving the junction. So if you have something of this now, of this nature, so you can have something like this. So let's say you have this arrow here. When this current is coming through this way, when it gets to this part, what will you have to do? It will have to split like this and split like this. So if you call this one I1, if you call this one I2, and if you call this one I3. So you notice that I1 is entering the junction, and I2 and I3, they are leaving the junction. So you have something like I1 minus I2 minus I3 will be equal to 0. So that's basically what the first law is saying. The second law is talking about total voltage in a loop. So if you have a loop in a circuit, that is, if you're able to like loop a particular path in a circuit, a closed loop. I think I explained closed loop earlier in the class. So the total voltage, summation of the voltage there will be equal to 0. And this is the way we analyze it. It depends on how you are moving in your path. If for cells, if you are moving from, if you notice that your movement, when you draw any straight arrow, directly in between the positive and the negative terminal, if you notice that your movement is such that you are going from negative to positive, in that situation, your value of the EMF in the cell is going to be a positive value. So you have a positive voltage. But if you notice that your arrow is drawn such that you are moving from the positive terminal to the negative, I'm talking about right in between the positive and negative terminal now. So your value of voltage is going to be negative. Of course, I will explain this using an actual example. So it is going to be a negative value. And for any resistor, of course, the voltage in any resistor is given by IR. So we always consider resistors that there will always be a voltage drop in resistors. So therefore, they are always negatively represented. So let's consider a sort of example of what I'm trying to say now. So let me just quickly get that example right away. Just a moment. Okay, let me put this right here. So I'm going to be using this now. So I will use this to explain everything I've said about the old Kirchhoff's rule and the likes. So the first thing I want to take note here is that let's look at this voltage thing I was trying to explain earlier. So if I want to choose a loop now, let's say I want to choose this particular loop now, the loop FEDC. So I can consider that for this guy now, I can decide to travel in this direction. So that means that as I go in this direction, I will also come down here. I will also go in this place. I will also go in this place. That is me covering the loop, FEDC. But I can also choose the other path. I can say I want to go in this direction, in this direction, in this direction, and in this direction. So it doesn't really matter. But I'm going to explain something else later. So if I'm going from this now, from this guy to this guy, it implies that I'm having a positive voltage. That means that my arrow is going directly from a negative to what? A positive terminal. But if I'm going in this part now, instead of this 20V that I have now, I'll be negative 20V because I'm going from a positive terminal to a negative terminal. Now, this is very good when you have two cells like this actually, where one of them has to be positive and the other has to be negative. So one of them has to be positive, the other has to be negative. When you have such loops, then you need to really, really consider what I just explained here. Now, what do we actually always choose? We always choose that our current is leaving from the positive terminal actually. So therefore, if I want to move now, if I want to move from this 20, I will have to move from this positive terminal and move like this, because we always choose that current is flowing from the positive terminal then going to the what? Negative terminal. But if you look at it, I have two cells there. One is of 80 volt, one is of 20 volt. So it is better I choose the one with 80 volt in this situation because it is of higher voltage. So therefore, that will give me the first perspective as the positive guy. So anyways, that's that about that. Now, let's now apply Kirchhoff's rule. Let's apply the first rule. I want to pick this junction. Let me use another color. So if I'm picking this junction now, so let's see what is going on there. I want to go against the arrow that has been drawn in the question already. I just want to use my own arrow. So that implies that I'm saying that there is current going in this direction. So let me call that current I3, still I3. And there is, so when you get to this junction, there's going to be a splitting. One will go in this direction and the other one will go in this direction. So this one, let's call it I1. This one, let's call it I2. So from what you know about this, I've explained already. I3 is entering, so that will be I3, and I1 and I2 they are leaving. I3 minus I1 minus I2, that will be equal to 0. So there implies that I3 equals I1 plus I2. So we have been able to sort out the current, so and that's the entire current that is flowing in the circuit. So all of them are well represented: I1, I2, I3. So if I choose the first loop now, like the one that I've been explaining already down here, so I want to choose the 80 volt part to determine whatever it is I'm doing. And then I will choose this direction of flow. So I will have to follow the arrow that has been indicated already. So current is flowing from this place now. So let's start with the 80 volts. So with the 80 volts, I will have a positive 80 volt. So that will be 80. I think I should use a different color. So that will be 80. Now, when I get to this 20 ohm now, like I said, for resistors, you always have a negative 2. But what current is flowing through there? I2. So we have negative I2. V equals to IR. V equals IR. So that's basically what I'm using. So I2 multiplied by 20. So let's see, we got to this place again. So you can see that following this path now, this 20 volts is also traveling from negative to positive. So therefore, I'm going to have a positive 20 as well. Positive 20. So that's basically what I was trying to explain here. When you move from negative to positive, you use a positive value. When you move from positive to negative, you use a negative value. So if this guy had been reversed, that would have been negative 20 volts instead. But because it is still like I'm moving from what? Negative to positive. So it is still what? It is still positive. And then, so I'm done with this. Let's get to this guy now. I3 is what is flowing in it. So we have negative I3 times 20 as well. I think we're done with everything in this place. 1, 2, 3, 4. We have 4 elements there, so we're done. Everything here will be equal to 0. So I'm done with that loop now. So let me just finalize it. So that implies that I have 80 plus 20 is 100. So that will be 100 equals, if I take all of these guys to the other side, that will be 20 I2 plus 20 I3. So you can divide both sides by 10. No, by 20 actually. So this will be 5 equals I2 plus I3. Let's call this equation 2. This will be our equation 1. Now let's analyze another loop in that case. So let's analyze this other loop now. So we have 20 volts, we have this. So let's move in this direction, So we have, first of all, we have 20 volts there. So that will be 20. Then when we get to this guy, that will be negative, what's flowing through this place? I3 times 20. Then we get to this resistance as well. What's flowing through it is I1. Like I1 is also what's flowing through it. Don't really like bother yourself too much about that. So I1 is going to be the one flowing through it as well. So that is going to be negative I1 multiplied by 30. There are only 3 elements there in this loop, so this will be equal to 0 as well. So when you do that very well, you're going to get that 20I3 plus 30I1 equals 20. And then when you divide through by 10, you have 2I3. So you have 2I3 plus 3I1 equals 2. Yeah, equals 2. So we have everything that we need now. So let us solve this simultaneously. From the first equation, I1 plus I2 equals I3. So let's solve everything together. So what we can do here is that we can decide to make I1 the soluble formula here. So I1 is the same thing as I3 minus what? I2. So if I substitute that into this place, so that will give me 2. Then we have, oh sorry, that will be 2I3 plus 3I3 minus I2. So I'm substituting I1 now, I'm replacing it with I3 minus I2. So you have 2I3 plus 3I3 minus 3I2. Everything is equal to 2. So when you do that together, you have 2I3. So that will be 3. No. So we have 2I3 plus 3I3 now. That will be 5I3 minus 3I2. That is equal to 2. 5I3 minus 3I2, that is equal to 2. So when we have this now, don't forget we already have a I2 plus I3 equals 5 before. So that implies that I can easily say that I2 equals 5 minus I3. That is from this place. So with that, anywhere I see I2, I can replace it with 5 minus I3. So 5I3 minus 3, 5 minus I2, everything here will be equal to 2. So let me confirm that. Oh, sorry, 5 minus I3 rather. 5 minus I3. So this will be 5I3 minus 15 plus 3I3 equals 2. So therefore we have that 5I3 plus 3I3, that's 8I3 equals 15 will go to the other side, that will be 15 plus 2, that will be 17. So I3 equals 17 over 8. And 17 over 8 equals, let me press my calculator for that. 17 divided by 8, that's 2.125. 2.125 ampere. Then the other guy, so if that is 2.125, I can easily get my that was I3 anyways. I can easily get I2. So I2 will be 5 minus 2.125. So 5 minus this guy is 2.875. And earlier we said I1 is I3 minus I2. So I3 itself is 2.125. So 2.125 minus 2.875. That's negative 0.75. So I1 will be negative 0.75 ampere. So why did we get a negative answer for I1? It means that the path that I chose is not going to be a correct path. So that implies that this actually is not going in this direction. It is actually moving in this direction instead. So it is okay if you get a negative value for your current. It just means that the path that you chose, you should have traveled in the opposite path instead. And that's basically how you apply the Kirchhoff's rule. And that's going to be it for DC circuits. Of course, there are other things, but this covers the basic thing that you need to know so that you understand everything better. That's it for today. Make sure you like this video and you subscribe to the channel. I'll see you in the next one.